Here we talk about the role of the direct air capture involving the 21st century energy system. Before his talking, I'd like to briefly introduce uh, him. His research interests include the carbon cycle by carbon dioxide capturing from the air and carbon sequestration, and also carbon footprint, innovative energy and infrastructure shifts, the role of the automation, robotics, and the mass manufacturing in massively parallel infrastructure system, and also energy and environment policy. As you can see, his research covers the almost full system of energy society. And so his talk is related to direct air capture. So I'd like to briefly our current, the reason why today we have his seminar. So, but before starting his lecture, I'd like to ask you, all of the participants, um, here, this seminar will be recorded and made available on the I²CNER website later. And also because of the Zoom system, so I prefer to have a Q&A session after his presentation. So if you have a question, or please type your question, comment in the Q&A box, or you can simply push the raise hand button and unmute yourself after the chair assigned you. So the reason why today we have this special seminar is, Kyushu University were awarded of the Moonshot project. Actually, what is this? What is the Moonshot project? So the Cabinet Office of Japan launched the Moonshot Research and Development Program, and sorry. And this program is set a very ambitious goal to attract the people and promote the challenging research and development project with the aim of resolving the difficult society issue while bringing together the wisdom of the researcher from all over the world. So Japanese government put the 7 moonshot goal. So among this goal, moonshot goal number 4, we Japanese government put some target about the realization of sustainable resource circulation to recover the global environment by 2050. So we have 2 major keywords. One is cool earth and clean earth. So concerning the cool earth, so our Japanese government want to develop the circulation technology on a pilot scale for the reducing greenhouse gas that is also effective in the terms of the life cycle assessment, LCA, by 2030. So in this project, in this goal, direct air capture is a very essential and central keyword because we have already emitted large amount of CO2 in the atmosphere, and also we have to manage this carbon capture, carbon, and also circulate in our society. So under this program, we propose so-called MOSES project, Moonshot for Zero Emission Society project. Kyushu University is a representative institute, and in this project, innovative membrane separation unit and electrochemical or thermochemical CO2 conversion unit are integrated as one unit, as shown here. And then we put the name of this system, so-called direct air capture and utilization system, DACU system, that can process the CO2 capture from the atmosphere and to carbon fuel production continuously. So, and also this is very important of this project. DACU system with a highly size scalable feature will be dispersely deployed and contribute to the construction of carbon recycle society based on the local production for local consumption. Actually, this is small scale, but we can combine them as you want, like shown here. So this size flexibility would provide more opportunity to capture the carbon CO2 in even the urban city. That is our project target. Of course, this project, direct air capture, is a very important keyword and central issue. And that is why today I invite the Professor Klaus Lackner from the Arizona State University, because he is the first person to suggest the capturing the carbon dioxide from the air in the context of addressing the climate change. This is actually just copy paste from the Wikipedia. But also scientifically, they are recognized. For example, say you can find his name, a lot of paper. For example, say chemical review paper, a concept that was first introduced for the climate change or mitigation by Lackner in 1999. As you can see here, he is a truly first researcher to propose the concept of direct air capture. So of course, he is a ongoing researcher. That is why I'd like to hear or listen his concept and also current cutting edge research. So today he will talk about the role of the direct air capture in the evolving 21st century energy system. So I'm very happy to invite the Professor Klaus Lackner. So Professor, please.
Thank you so much for having me here today. And I first need to get my PowerPoint going. See that I can make this work. And now I have to go to slideshow. So can you see me? Can you see this? Does it work? Okay, very good. Thank you very much for having me. And I have gotten involved into the issue of carbon management by now about 30 years ago, in the early 1990s. My first question was, where do we put all that carbon? And now I'm trying to figure out, where do we get all the carbon from? And this is, of course, direct air capture, which is what we are going to talk about today. But I really entered this discussion, not so much from the climate side, but the realization that energy is critical to human well-being. We need to figure out how to have energy for people. Energy makes modern life possible. It supports access to food. Think of Haber-Bosch, the Haber-Bosch process for the nitrogen fertilizer, for refrigeration. For all of these issues, we need lots of energy. It cleans up and transports water. It opens dilute mineral resources. You can use copper and nickel and platinum because you can mine vast amounts of rock and grind them finely and spend a lot of energy in this process. And of course, if you want to clean up after yourself, it typically takes energy again. You're fighting entropy or you pay for workarounds, and at the end, this always costs you energy. Lastly, what motivated me a lot is if you look at the world, we managed to stop the population explosion wherever we had a decent standard of living. It seems they correlate tightly together. Probably it is the secure standard of living and good education, particularly for women, which in the end manage the population and stabilize it. It's stabilized in Europe, it's stabilized in the US, it's stabilized in Japan. And developing countries have a challenge they still have to overcome. So if we want to stabilize this sustainability issue, we better figure out how to have a decent standard of living, which in turn requires energy. Now, if you look at energy for the last 200 years, we have relied on fossil carbon. We first started with coal, then we added oil, then we added gas. And we are now at a very new transition. And I would argue the biggest player in this transition is actually solar photovoltaic energy that is challenging the status quo. After decades of effort, the solar energy today is competitive with other options. The levelized cost of solar energy by now has dipped below the dispatch cost of fossil energy. In other words, solar panels are cheap enough that they can run against the gas-fired power plant. Of course, they only run part of the day, and this is the new challenge of dealing with the intermittency. Without any climate concerns, this would provoke a revolution in the energy system anyhow. But this is complicated by the fact that climate change requires a rebuild of the energy system anyhow. The world simply cannot keep dumping CO2 into the atmosphere. And the time we have available to act here is very, very short. and we are already committed to large-scale negative emissions. We are too late to simply stop emitting. We need to clean up after ourselves. And at the same time, I think it's a fair guess that fossil fuels are not going away quietly. They are not going to run out. This was a mistake in the 1990s that people thought we are just about out of fossil carbon. We keep finding more and more. So this is not self-limiting. And on the other side too, liquid fuels are extremely useful for transportation and long-term storage. And so it's very hard to figure out how to get rid of them. But on the other hand, you have low-cost solar technology and incumbent fossil fuel that's hobbled by climate change. So the result is that we will have to figure out how to do this. And keep in mind, the last 20% of power tends to really like liquid fuels, and therefore it's very challenging if we don't have those. As I noticed, we really don't have much time to waste on this problem because the 1.5 degree warming, and I'll just explain this a little more in a minute, is literally upon us. We are very, very close to being there. There's very, very little time left to stop. We cannot wait for economic drivers because CO2 becomes interesting and we solve the problem because it's economically appealing. We will have an overshoot. It's more than just likely, in my view. And regulation of CO2 emissions is absolutely critical. My approach to this actually from the beginning has been to think of CO2 as a waste management problem. It's not just a mitigation problem. We are dumping CO2 into the atmosphere and we need to stop that. We have done this for sewage, we have done this for municipal garbage, and it is now time to demand that every carbon that comes out of the ground, an equal amount of carbon will have to be put back and safely removed. And honestly, in the long run, you will have to remove more. Moving to a waste management paradigm represents a very big shift. If you think about it for a moment, we are in a waste management paradigm, you are not allowed to dump, which is very different from saying we need to reduce like next year by 10%. It is an enormous transition where we have to clean up every little bit and probably have to clean up the litter, the dirt we have left already in the atmosphere. People argue, should we reduce, reuse, and recycle? Yes, of course we should. That is a good idea. But at the same time, we need disposal. So far, and this is the standard approach, the mitigation approach we have taken, we say, let's reduce, let's reuse, let's recycle, and then we can't quite figure out how to do it, and therefore we are allowed to put it in the atmosphere. In a waste management paradigm, whatever you could not reuse and recycle, you need to dispose of safely and permanently. And the cost of disposal, of course, motivates reuse and motivates reduction in emissions. And zero waste is a very nice long-term goal, but that comes after the cleanup. First, we have to stop the emissions and clean up after ourselves. And then we have to figure out how to make less emissions than we did in the past. To see how fast you have to be, and I nearly need to apologize because the initial graph was done in 2019, I plotted here a curve where on the one line, I show the targeted limit for CO2 concentration, let's say 450 ppm or 650 ppm. And then I asked the question, how much do you have to reduce the carbon intensity of the world every year to achieve this goal? In that process, you will overcome population growth and economic growth of roughly 3%. And if you wanted in 2019 to stop at 450 ppm, you would have to reduce the carbon intensity by 9% every year. And even at 750 ppm, you would have to reduce it by 3.75%. This is far more than we historically have ever done. I took a similar plot like this and I said, in all likelihood, we will keep ignoring this problem. Energy consumption will grow for 2% a year. And so if we change our mind in 2020, how much do we have to reduce every year to stop at 450 ppm? And now it's 9.6%. If we keep talking about, by now it's, by the way, 10% because we're in 2021. If we keep talking about the problem until 2025, the annual reduction required to stop at 450 ppm would be 14% per year. And that is simply not practical. So we live in an overshoot world. We have gone past this point. And to just see that I'm not unreasonable with my simple calculations, which are based on CO2 concentrations in the atmosphere and how they change from year to year. Here are the IPCC reduction curves to stay at the 1.5. And in most scenarios, the 1.5 degree is a little below 450 ppm. So you're a little more aggressive. And here is my 9.6% annual reduction overlaid on this. So what you are seeing is my numbers, even though they are very simple-minded, are in the same ballpark as the fancy computational models. But of course, I don't allow for dealing with an overshoot because I'm only reducing in this model. And furthermore, I am going for 450 ppm, which is a little higher than you would otherwise be allowed. But again, it shows how unrealistic the idea is that we can just have a magic wand and tomorrow we're going down to these levels. We actually live in an overshoot world and we have to figure out how to come back, and that will require negative emissions. And you would like to have a closed carbon cycle that is supported by renewable energy. Once you are there, you actually don't need fossil carbon anymore. And if you look at it from that perspective, the inputs in such a world are carbon dioxide taken from the air. For that, you need direct air capture and maybe some biological processes, but it's new technology which is absolutely pivotal for that concept. We will need the ability to pull carbon dioxide back out of the air. Then we need hydrogen, which we can get from water. And that's an old technology. Electrolysis has been around for 150 years, but the capital cost is too high to support intermittent systems. So we have to learn how to make that better than it is today. And ultimately, we need energy. And here I'm suggesting your solar photovoltaic panel is a likely candidate for that. We have seen a consistent cost reduction of about 24% every time the number of solar panels doubled. And if you will simply want to saturate the market with solar energy, you have 5 to 10 more doublings in front of you. Now, whether they each give you another 24% reduction, nobody knows, but it promises that the cost of electricity will go well below 1 cent a kilowatt hour. You still have to to manage intermittency, and you need hydrogen production with cheap conversion devices. If you can do that, you can close the cycle. And here you see the dramatic cost reductions in photovoltaic. The cost of a solar panel today is less than 1% of what it was in the 1970s. And it's by the way a power law, and if you grow a millionfold, the energy cost, the solar panel cost drop to 100-fold, which is a nice 1/3 power law. The closed carbon cycle you can support by renewable energy. The output then is electricity for direct use and for batteries. If you deal with short-term storage or you immediately use it, this is where the power should go. For the longer term, you can make synthetic fuels for transport and for long-term energy storage. Think about being in a winter rainy place and you use solar energy, which came from a sunny place 6 months earlier, where you can now run power plants, which stored energy literally from summer to winter. That's technically feasible. And if you think about it for a moment, it completely eliminates the intermittency challenge because you basically intermittently make fuels and you can now use them. The market has to find the optimal penetration of fuels. These fuels are relatively speaking expensive, and therefore the optimum is probably different than it is today. But beyond that, you're also producing excess CO2 if you choose to, and that is for long-term disposal. If we want to restore the climate to what it was before, we will have to get back probably by 100 ppm, at least order of magnitude. And that means we have to find a storage for 1,500 gigatons of CO2. That's 100 ppm in the air. I don't know how this just worked. So you can think of a system which has air capture, renewable energy, and water processing, It has electrolysis and synth fuels. In the electrolysis, releases the oxygen back into the air. And in the combustion process, it makes water and CO2, which then are recycled through the system. What this gives you is electricity as an energy carrier and liquid fuels. The electricity you can distribute, it's clean at the point of consumption. It works instantly on demand. And it's rarely converted to fuel today because you wouldn't do that because it's too valuable. Liquid fuels, on the other hand, are easily shipped and transported. They store energy for, if necessary, for years, and it's easily converted to electricity. But the CO2 needs to be managed. What's missing to make this work is electricity to chemicals. Electrolysis needs to have a lower capital cost than today, and I'm happy to explain that. And electrolysis is too expensive, but at the same time, Fischer-Tropsch processes need scaling down, and you need a closed carbon cycle via the air, and this is what today's topic is about. It's also very clear, at the end, this is roughly a 40 gigaton a year challenge. If you look at it, I can give you this number 3 ways. Currently, we are emitting roughly 40 gigatons of CO2 per year. So if you wanted to match that, that's what you need. If you think that in the end, the last 20% of the energy economy should end up running on liquid fuels, because that's the part which is very, very hard to clean up. By 2100, that last 20% will be 40 gigatons of CO2 per year, because 2% annual growth over 80 years is a factor 5. So carbon dioxide drawdown, on the other hand, also would require 1500 gigatons of CO2, and with a little bit of an arithmetic inaccuracy, that's about 40 gigatons of CO2 per year. We need scalable options, which are at a very, very large scale. If you wanted to do this with biomass and you wanted to get sunshine into biomass, you are talking about a scale which is larger than the world's agricultural land. So we need to have technical solutions to this problem. On the other hand, I doubt that we give up on liquid fuels. Trucks and ships and airplanes really do well on it. And liquid hydrocarbons trade at an enormous premium over other forms of energy. Oil relative to coal is roughly 6 times as expensive, and it's 3 times as expensive as natural gas. And that reflects its convenience of being a liquid. The value derives from the ease of transport, storage, and use. It has an energy density which is 2 orders of magnitude larger than that of a battery. The tank is cheaper than its content, and that minimizes capital tied up in storage. And the inert liquid is easy to handle and introduce into energy conversion machinery. Right? It's easy to ship or pipeline. And because of all of these things, this is a really good example why you would like to figure out how to have access to liquid fuels. Our solution is to collect the CO2 from the atmosphere and then figure out what to do with it. We call this a mechanical tree. Here is a drawing of a concept which we are now trying to realize in a first prototype. We basically have these disks where the wind blows in between, and the CO2 gets stuck on the surfaces of these disks because they are made out of sorbents. And the mechanical trees are about 1,000 times as efficient as a planted tree to collect CO2. It's passive in the sense that we don't blow air around. We argue it's going to be affordable, and it's a rational means to address the existential threat of global warming. A dozen of these trees, about 10 meters tall, 1.50 meters in diameter, would collect a ton of CO2. They collapse into that drum at the bottom, which is about 2.5 meters tall. And so as a result of that, you can pack a dozen of them into a single shipping container. Also, they are quite compact at the end of the day. Solar or wind farms can provide the energy to recycle CO2 and water back to fuel. The mechanical tree farm, which would support that effort, is actually a lot smaller than that solar farm or wind farm, for that matter, which would provide that energy. So they are actually, from that perspective, scalable. They are scalable, they are flexible, they have minimal environmental impact. We can deliver the CO2 drawdown at the necessary scale. We could, at a similar scale, provide the feedstock for renewable synthetic fuels, and we can clean up the carbon waste. It would help renewable energy to replace fossil carbon, because renewable energy could now enter the liquid fuel market just as well as the electricity market. And that's the promise of direct air capture. And I would point out that I was chagrined from day one when people call it geoengineering. It's not. It's mining CO2 for useful purposes, closing the human carbon cycle, or for that matter, cleaning up our litter. But we are not geoengineering the planet when we do that. So there are questions whether it's even feasible. And the answer is, yes, it is. The CO2 in the air is not too dilute. 1 cubic kilometer of air, and I make a comparison to wind here. 1 cubic kilometer of air, it passes through a big windmill in an afternoon. And if I value the kinetic energy at 5 cents a kilowatt hour at 6 meters a second wind speed, I have $300 worth of kinetic energy in that cubic kilometer of air. If I pay you a tipping fee of $30 to get rid of the CO2, that CO2 in that same cubic kilometer is worth $21,000. So I would argue, as a source of CO2, the air is 70 times more valuable than as a source of wind energy. Yet we have learned how to harvest wind energy quite routinely, and we are very good at it. So now I would argue we have to learn to do the same here. The area demand of air capture is actually quite small. It's 3 orders of magnitude smaller than biomass generation. That's why it works. We end up with 1 billion such trees. People want to solve the problem, but with natural trees are talking about 1 trillion trees. 2 orders of magnitude smaller than wind installations, and 1 to 2 orders of magnitude smaller than solar installations. And I would argue direct air capture at this point has no good substitute. People have asked me, are you sure it will work? And my answer is no, I'm not sure it will work. But I do know if it doesn't work, it's going to be painful because we do not have a good substitute for it. So if we want to close the carbon cycle through the environment, we actually have options. We can go after the biosphere, and we collected the carbon via photosynthesis. We can do that. We can store bioenergy with CCS. We can do reforestation. We can produce biochar. It's affordable. It's a great start. We should do it, but it's ultimately limited in scale. You would need more land than the world uses today for agriculture, while it has to feed more people than today to make this work. So I think this will be a player, but it will be a small player. From the ocean, you can do carbonate chemistry. Thermodynamically, that's identical to get it from the air because the ocean and the ocean water and the air are in equilibrium. But in the water, there are 25,000 water molecules per carbon molecule. Whereas in the air, it's 1 in 2,500. I actually think for that reason, air capture is easier than ocean capture, but if you have a good idea of how to do it from the ocean, I would argue it's a parallel, comparable approach to the problem. So there are challenges though. What's the economic pull? The use of CO2 is too weak a pull. The unfortunate truth is a lump of coal is always cheaper than CO2 from air, and therefore it will only work if it's waste management as a service that requires regulation. And then, of course, it allows you to close the carbon cycle because the alternative is that you pay for the waste disposal. You must make it necessary via regulations. Ultimately, the carbon price, which comes from regulations, must exceed the cost of air capture. However, I would nearly turn this around. I would argue at the end of the day, the cost of air capture will set the cost of carbon. And of course, the lower, the better. But if you have a technology, if you must collect, if you have a technology that's cheaper than air capture, it comes first. If you have a technology, because you could do it at a power plant. If you don't have a good option like an airplane, then air capture will be the option of choice. And if you have an option which is more expensive than air capture, why not use air capture? The logistics of deployment is going to be absolutely formidable. You need to grow from nothing to gigatons in a few decades. And there's still technical challenges. This is new and innovative stuff, and it's far from clear. So people have actually said, is it really feasible? Right? And clearly 400 ppm poses a serious challenge. CO2 is dilute and the air is full of water, but I couldn't resist to these two pictures. You see a bird and you know that heavier than air flight is possible. You see a tree and you know that that direct air capture is feasible. And this is a colleague of mine, and he stands in front of the first prototype in 2007, where we actually made it work. So the thermodynamics is not limiting us. People have argued this. Here is the complete formula of the Gibbs free energy of unmixing or mixing, whichever way you choose to look at it. And if you want to go and remove CO2 from the atmosphere, it takes 22 kilojoules per mole. If you burn gasoline, you get 700 kilojoules of energy extracted. So you're at about 3% thermodynamic penalty simply from the thermodynamics perspective. In practice, all existing processes fall woefully short of this number. They need a lot more energy. But that tells you that we have still a lot to learn, because in the long run, good technologies gradually approach the thermodynamic limit. And if you're 20, 30 times off, you have a long ways to go, and eventually you may find yourself 2 or 3 times off. And at that point, the cost of energy is not what limits you anymore. People have argued the Sherwood's rule, because Sherwood has said that the cost of separation is linear in dilution, and we know what it costs in a power plant, therefore it's hopeless here. Sherwood's rule is correct, but it applies in a funny way in saying that if the first step of the cost dominates everything, then you are in trouble. And air capture is clearly too cheap. But colleagues of you in Japan have worked out that you can extract CO2, uranium from seawater at 3 parts per billion. And the trick was to be passive. Once you didn't pay for pumping the water, you could afford absorbing the uranium on a sorbent, a resin, by the way, and then destructively process the resin for its uranium content. And while the cost is still a little higher than mining uranium, it is actually quite close, and it's far from Sherwood's rule. Air capture, besides, is real. There are several startups who are working on it. You have heard about Carbon Engineering, Climeworks, Global Thermostrat, and ASU is involved with a new startup called Silicon Kingdom Holdings. And our goal is to actually make this work. All of these have worked on designs. Ours is passive. The others are blowing the air around. Here is an early prototype. On the left, it's a picture of a device we had for a year, nearly a year outside, and it actually collected CO2. On the right, you see an artist's rendition of the next version we are building. We are right now have a concrete pad on campus where this year we are going to build that next system. Our systems are passive. We use moisture swing to make it work. And we use a thermal swing sorbent as another alternative, and we have some innovative membrane designs we are pursuing. We are aiming for a mass manufacturing design and a 2-stage concentrator where we first go from 0.04% to 4 or 5% and then jump all the way to pressurized CO2. Our goal is to make direct air capture affordable. The moisture swing is an interesting thing we discovered somewhat serendipitously. Certain ion exchange resins, strong-based ion exchange resins, have the feature that when they are dry, they love CO2, and when they are wet, they don't have any affinity to it. And we discovered this when we put these anion exchange resins into their hydroxide form. They loaded up to become bicarbonate, and if you made them wet, they fall back to the carbonate. They literally, the partial pressure in equilibrium over the resin increases 500-fold as the relative humidity goes from 25% to 100%. We can characterize, therefore, the free energy of binding as function of the relative humidity, and you notice it changes by on the order of 12 kilojoules. So this is the difference between having 4 or 5% CO2 over the system or 0.04%. We can use water, moisture to drive CO2 off the system. We created numerical simulation models which allow us to understand the transport inside these materials. And we found something remarkable. If you make a membrane out of this material and you make it wet on one side and dry on the other, not surprisingly, water follows the gradient and goes from the wet side to the dry side. But that water flow literally pushes CO2 uphill, because on the dry side, the concentration of CO2 in the membrane is high, and on the wet side, the concentration of CO2 in the membrane is low. And as a consequence, there's a gradient. The CO2 falls down and goes out on the other side. The energy for this pumping up of CO2 ultimately comes from diluting water into the atmosphere. So as a process, we are now thinking of hollow fibers, think of straws, leaves, surfaces, where on the inside we have a carbonate solution which turns itself to bicarbonate, and that way we can collect CO2. We are working on developing that process. We have made significant progress over the last year, but we are not quite there yet. There are plenty of challenges for air capture. It's a novel technology. Lots of things still need proving. We did some techno-economic assessments. One of my former students, Habib Asarabadi, pointed out we need about 100,000 cycles in the life of a solvent in order to make it economic. We need to be able to clean off SO2 and other sour gases, which we will pick up from the atmosphere. And of course, we need to manage water. So there are lots of opportunities for new research, great new ideas of what to think about. And maybe we can also deal with power plants, because if you have a peaker plant, you can't afford putting things on there. The other challenge is, of course, you build a new industry from scratch. The cost has to come down, right? Supply and demand will set prices, and you have a large buildup in a decade or two. The climate change will drive demand at high prices. Deep penetration of renewables requires, however, a very low price for direct air capture. I mean, the high price of CCS, in my view, will likely drive renewables forward. And we should couple those two things, have renewables, or for that matter, nuclear energy, work with direct air capture and make this work. And I would argue the need for drawdown, the need for negative emissions will keep the price of carbon storage high, because you have a built-in demand which will not go away. How do we get to low cost? Well, when we started, people said $600 is the floor. Early implementations now claim something like $200-300. Carbon engineering claims they can get all the way down to below 100. I would argue practical interest starts at 100 tons, because above that, I think it's too expensive, except as an emergency means. On the other hand, you can look at our work, and you'll find that the raw materials and inputs we need, sort of the frictionless cost, if everything could just be piled up, those raw and energy costs are somewhere between $10 and $20 a ton. At that level, everything else, in my view, can be learned away. And so I still see no reason why, once we reach gigatons, we couldn't be at $30 a ton, but of course I cannot prove that. On the other hand, you see that photovoltaics has shown the way. Direct air capture is just entering the race, and the starting point for us is, of course, much better than for renewable power, right? Because we need to only get 10 times cheaper. The world is right now at $500 a ton, and at $100 a ton, we would be great, and at $50, we would be really good. Photovoltaic did succeed in gaining a factor 100, for which it had to grow 1,000,000-fold. So if you have the same kind of power law, and here I use this 1/3 law, air capture would have to grow roughly 1,000-fold. So from the kilotons per year to the megatons per year, whereas PV had to grow 1,000,000-fold to get from kilowatts to gigawatts before it was there. We said, what if you hypothetically subsidize the excess cost and pay the producer as a subsidy anything above the target price of, let's say, $100? If you follow conventional learning curves, which is an if, you find that for roughly $50 million, that's the black curve in the middle, you actually would hit your target with 50% probability. Now, if you do the Monte Carlo and estimating how all these parameters could be logged normally distributed around that, you find that you have a long tail where you get to exceedingly high costs, which basically says learning models don't apply to this technology, which is a possibility. And in that case, you would know after a few billion that you clearly wasted your time and money, and you should not do this. But I think it is worth a few billion to figure out whether this technology is available. And I think you need to set early cost targets. I think for raw energy from a PV panel, 1 cent per kilowatt hour is a nearby target. As a matter of fact, I'm arguing they're not far from there because people bid at 1.5 to 2 cents a kilowatt hour to get on the grid. If I remove the inverters, people tell me it's half of that price. So we are close to a cent a kilowatt hour. You need to be below $100 per ton of CO2. Now, a penny a kilowatt hour at 50% efficiency would cost 80 cents to the gallon, or roughly 20 cents to the liter of gasoline, and CO2 at $100 would be comparable. The problem is your electrolyzer. At 10% utilization and $100 per kilowatt, that still adds 80 cents. And your current electrolyzers have a capital cost somewhere between $500 and $1,000 a kilowatt. So if you want to live with intermittent energy, you have to mass produce those as well and get the price down below $100 a ton. But if you look at Fischer-Tropsch or methanol, we can do that, and it's cost effective at large scale. But if you deal with solar panels, you have to scale down. But if you look at and add up these costs, you come out at costs which certainly after taxes are smaller than current fuel prices. So I do believe we are getting close to being able to do that. So there's an enormous economic opportunity. Carbon dioxide is always more expensive than fossil carbon, so you need the climate change perspective. And managing CO2 is a waste management challenge. And I think you need to introduce the concept of certificates of sequestration. And you need to demand that carbon coming out of the ground needs to be cleared by a certificate of sequestration. And if you do that, then markets can figure out the lowest cost option. I'd be willing to bet that that will include direct air capture, but the markets will figure this out. And it introduces uses for excess carbon, and it supports the avoided cost of disposal. And renewable energy will drive us to zero waste. We use, recycle, and dispose 50 years of past emissions, because that's what it will take to stabilize the climate. Air capture then will set the price of carbon. And I would argue waste management of CO2 can become $1 trillion business, which puts it in the same ballpark as automobiles or aviation, or a little smaller than the world energy systems. Then you can have a closed carbon cycle. About 20% of the energy will likely flow through hydrocarbons, and photovoltaic power can capture this market. And I think we enable photovoltaics or renewables in general to really deeply penetrate in the market, because we take the intermittency away. You have to get from kilotons to gigatons at the end in order to be practical. The commercial markets are in the megatons. The US is consuming some 7 million tons of CO2 as merchant CO2 a year. That price is between $60 and $300 a ton. There's a large geographic difference. It depends how long the ride in the truck is. That gives you a foothold for a new technology at the megaton scale. Then you need regulations to get to the gigaton scale. Can you get there? 100 million container-sized units with each 1 ton a day would keep up with 40 gigatons or 36 gigatons actually per year. If you have a 10-year lifetime, that means you need to build 10 million of them a year. Shanghai Harbor processes 30 million shipping containers a year. They are full. The world produces nearly 100 million cars and trucks a year. So that scale is doable, provided we give the right incentives to make it work. How long will it take? I don't know the answer, but I can look at economically interesting technologies. There's a time they get invented. In this case, it was maybe 1999. There's a time it gets its start, the automobile, maybe 20 years later, and 25 years later, it's everywhere. Jet planes took a decade. Television stood for 40 years, but then in 15, 16 years, it was in the system. The internet, similarly, 25 years of being invented, but nothing happening. And then 16 years, it's everywhere. Cell phones are similarly. So I do believe that if we set our mind to it, create the right economic incentives, you can make this work on a 20-year time scale. But then don't forget, you have 40 years of pulling CO2 back before you have things under control. This is not a silver bullet. This is a hard slog to go. But ultimately, the cost can come down through learning. At 100 million mass-produced systems, you have the same learning potential as you have for photovoltaics. And you should easily move from $500 to $100 a ton. But maybe you can do better. As I pointed out, it takes a factor 300 to get down a factor 5. And it requires subsidies there, but less than $1 billion is my view, and it's worth trying that. And I would love if people were to figure this out. Another way to start is with volunteers. The US has introduced what they call the 45Q tax credit. That's the number in the tax law. They say, we give you $50 if you sequester carbon. If an oil company would stand up and say, we can now do it at $100 and we'll pay 25 of those. And you, the volunteer, pay the last $25 of a ton of CO2. That would mean I would have to volunteer 6 cents per liter at the gas station to fill up, or 22 cents a gallon. That's the same kind of surcharge people pay for clean electricity. I think you could get volunteers. I think we would kid ourselves if we think that solves the problem, but it will change the political debate, because if there are people who say it can be done and it's easy and it didn't hurt, you start making progress in this direction. And I think I'm out of slides and out of breath, and thanks so much for your attention.
Okay, thank you very much, Professor Klaus Lackner. So actually, we are scientists, but also your lecture give us a very insightful viewpoint from the economical, energetical, social issue. I think many people have the question. So I'd like to take a question or comment from the audience. So if you have a question, please raise your hand button. Just okay. Okay. First, could you talk George Harrington? With unmute, please.
Hello, can you hear me?
Yep.
Yes, I can hear you.
So I didn't even realize I'd raised my hand, but I do have a question. So I was wondering about the cycles, I guess sorption desorption cycles. Are those through like natural fluctuations in temperature on like a day to night basis?
No, that in a roundabout way they could be, because we are very, very sensitive to relative humidity. But no, we are thinking about it as, in Arizona we're in a dry climate. So if we expose these sorbents to the wind, they dry out. And once they dried out at 25% relative humidity or less, and here you can have 5%, they bind CO2, and that hydroxide form we may have started with is moving all the way to the bicarbonate. And if we now expose it either to liquid water or to 100% saturated air, or a vacuum with 100% with water vapor in it and nothing else, it will let go of the CO2 down to the carbonate, and you can raise the pressure in the system to about 5 kilopascals. And if you heat it up a little, you can go to 10, 20 kilopascals, but that's the limit. So at that point, you now have a mixture of water vapor and CO2 you can process on through compressors or second sorbents, whatever you choose. We are preferring a compression train. And then process make liquid CO2. You got energetically halfway because it's logarithmic in the concentration, right? So by the time you got your first factor 10 to your first factor 100, you are halfway there. So as a consequence, that's how the cycle works. And we have to evaporate water because the free energy of compressing the CO2 comes from the expansion of the water vapor into the atmosphere. The miracle of the material is that it links the two, and it links them through the size of the hydration shells. The carbonate becomes unstable if the hydration shell is small, and a consequence of that is that it disassociates into bicarbonate and hydroxide by splitting one of the remaining waters. And that hydroxide wants CO2. And if you were to count all the water in the hydration shells, what you see is that the CO2, the carbonate had more water in the hydration shell than the hydroxide and the bicarbonate together. So the Chatelier's principle is obeyed.
Okay, thanks very much.
Okay, next, Ronald, Ronald, please. You can unmute.
Okay. Hello.
Yep.
Yes.
I would like to ask just a few simple questions. The first one being, you said in your presentation that you capture the CO2 directly from the air and then tend to convert it into hydrocarbon through the Fischer-Tropsch process. So I was wondering, how long does it take for you to, if you compare the timeline for the capture and utilization via the Fischer-Tropsch process in comparison to direct sequestration, what do you think is better in terms of removal of CO2 from the atmosphere for a longer time? Because if we go back to the Fischer-Tropsch process, you're going to produce hydrocarbons that are going to be burnt again to produce CO2. So I'm looking at sequestration as a longer term solution instead of the Fischer-Tropsch process through which you are looking at after direct air capture.
You're correct. I think there are two things we are trying to do in parallel. And air capture helps both. One is to abandon fossil carbon, petroleum, without abandoning liquid fuels. And you can do that by feeding hydrocarbons, which came from CO2 and water and renewable energy, back into the system. That will not lower the CO2 in the atmosphere, but it will stop its rise because you are not feeding more carbon in. On the other side of the equation, you will have to put CO2 back. Now, once you have completely made the transformation, you don't need to do any more of that. But in the meantime, we have an overhang in the carbon budget and we have to pay that back. And I would argue that's currently on the order of 800 gigatons of carbon dioxide, and we have enough momentum, we will push this past 1,500 gigatons, even if we try hard to slow down. On the other hand, if we don't slow down, if we keep using petroleum, which is an option, then you have to keep putting probably 5,000 gigatons away by the end of the century. And I'm arguing that is harder than it looks. I also would argue that I grew up with the oil. My adult life, you have seen oil crisis, right? I sort of was a student in the 74 time window. One of the things I learned, the oil price is driven by supply and demand, not by the cost of extracting a barrel of oil out of the ground. The Saudis can still do this at a few dollars a barrel. So what you really see is you have a market. Now, if you look at oil, that started very tiny. And by the way, in 1917, the USGS said, we are running out of oil, guys. We need to do something about it. Biofuels is the answer to this problem. It was in 17. And then oil production grew nicely with oil consumption. As a matter of fact, if you look at the BP annual reports, it's very nice that the amount of reserve has been 40 years And if it's 50 years, we have an oil glut. And if it's 30 years, we have a panic, right? But it's in that ballpark, and it has always been there. Which, by the way, also says we always live on Hubbard's peak. But that's an old battle. I lost my thread because I looked at the question. So as a consequence of that, we got to store carbon, and but the demand for storage is initially 1,500 gigatons. So if I discover a new field reservoir where I can store, why would I give you a break, right? I know I have 1,500 gigatons worth of customers. So the price of storage, in my view, is very likely to come down. So as a consequence of that, the incentive to drive petroleum out, because if you think about it, the two ways are exactly parallel. I'm bringing petroleum out of the ground, I'm using it, refining it, using it, and at the end, I need to do air capture in order to store it if it went through an airplane, for example, or a ship. Right? If you now say, alternatively, I'll take that CO2 and make fuel out of it, I can close the cycle this way. But I'm arguing, if somebody tells me I have to put 1,500 gigatons away and there are governments standing in line buying that, I don't get a cheap deal on that new petroleum. So I think we are walking towards a world where the energy transition gives us liquid fuels. I'm not sure the question here is whether we could sell that oxygen. Yes, you can. And I think at some scale that works. But if we have 40 gigatons of CO2, and therefore I'm not doing the arithmetic right, but order of magnitude 30 gigatons of oxygen, I don't think you have a market for that anymore. But at the smaller scale, of course, the overall economics would be improved by that. You could also come up with clever ways of using it internally for other things. But we are going to see a huge intermediate transition because you start at megatons and you can do all sorts of things. And then you go to gigatons. I've seen people who say, well, we're making hydrochloric acid. Sure, you can, but what do you do with 40 gigatons of hydrochloric acid? And the same oxygen, I'm not quite sure what we do with the 40 gigaton scale of oxygen. But on the shorter scale, in the early days, all of this will make you money. And every little bit helps because you are pushed on cost. On the other hand, I would say, let's get those cheap options going right away. I am not opposed to having bio-based systems go right away because they are ultimately affordable right now. Their problem is if you push to the 40 gigaton scale, they are going to be an environmental nightmare. And so we got to figure out when to transition. But we now live in an overshoot world, and that changes things. We are not thinking anymore, how do I stop? But what's the damage I do by letting the overshoot grow longer? Your penalty is that you go too high and you stay high too long. So we need to figure out how to shape that peak and shorten the duration in which we are living in an overshoot. And whether we are already in it or we are still a decade away from it is another long discussion to have. And the 350.org people tell me that we are already 65 ppm above. And the 450 people think we still have a decade or so wiggle room. I think the 350 is more likely right than the 450, but we don't know. We'll find out. And if we're not careful, we'll find out the hard way.
Donna, is it fine?
Yeah, it's fine. I have another question.
Yep.
You mentioned that you're using solvents. There's wet solvents, and then you said you had a wet solvent, wet swing solvents. I want to know what kind of solvents are you using? Are you using, for example, amine-based solvents or carbonate-based solvents? And then,
yes, go ahead.
And then you talked about using membranes for direct air capture. I want to know specifically what kind of membrane you're using, because you say that you're working on a research to create a membrane that uses bicarbonate. I assume you're talking about calcium carbonates and magnesium carbonates.
No. You are correct that just about all the sorbents out there are in some form or another carbonate bicarbonate chemistry, right? But your question really is, what's the counter ion? Now, the moisture swing is a strong base resin, and so far every strong base resin we tried has had that feature. Classic one is Dow's Marathon A. It's a quaternary ammonium ion attached to a polystyrene. The counter ion, when you purchase it, is typically a chloride, but you can also buy it in the hydroxide form. When we started, we said, surely this will absorb CO2 in the hydroxide form, and sure enough, it did. It was actually faster than hydroxide solution. But what was startling was that it went to the bicarbonate. It loaded up from the hydroxide to the carbonate, and it loaded up all the way to the bicarbonate, whereas a 1 molar or 2 molar sodium hydroxide or potassium hydroxide solution will stop at the carbonate point and is in equilibrium with air. You need 20% CO2 over it if you want to go further. If you look at this particular material, if you make it wet, so it's loaded with water, it behaves just like that sodium hydroxide solution, and the bicarbonate has 20% CO2 over it. If you dry it out, it wants that CO2 back, and it operates at a 500 times lower equilibrium partial pressure. And we track that down to the behavior of the hydration shells. As you shrink them, all ions lose energetically and go to a higher state. But the big loser is the carbonate. And so the carbonate gets destabilized relative to the bicarbonate and hydroxide, and the hydroxide has the strong binding energy. So that's how that works. Now, you can amplify this with a bit of a thermal swing, and our partner, who is headquartered in Dublin, doesn't want to be limited to desert climates. So they also look at sorbents, which are thermally based. And those are typically tertiary amines, but you have other options there as well. Lastly, your membrane. Our problem is, this started theoretically. I'm a theoretical physicist, so I can't help myself. We wrote down a transport model for these strong-based materials with an equilibrium equation and all of this, and we worked it out, and we got very nice agreement between the behavior of little spheres loading and unloading with CO2 as we expose them to variable moisture levels. And I said, what would happen if we make it a flat sheet? And then we found the pumping effect. It's like the thermoelectric effect, where heat flowing from hot to cold pushes electrons against the voltage. Here it's water going from wet to dry, pushing CO2 uphill. By the way, you can convince yourself it also goes the other way around, but that's not as interesting for us. But the net result is, this is the same ion exchange material. The only problem we have, and this is why we're working with polymers, with polymer scientists, the conventional ion exchange resin is as brittle as glass. And you can't make it into a flat sheet and wet on one side, because it expands by 10% in dimension, and that'll just fracture it. So our challenge right now is to make a new polymer which behaves the same way, but it's the same time still pliable. Or where we embed into a pliable structure rigid little discs of the material that have these transport phenomena. So that's what we're working on.
Is it okay?
Okay, one more question, please.
Yeah, we have one more question.
The last one. The last
okay.
one.
Short one, please.
You explained the economic aspect of the process, the DAQ, direct air capture and utilization. But something I need clarity about is when you compare the cost of the Fischer-Tropsch process, including comparison to current crude oil market prices. If you compare the hydrocarbons produced for the Fischer-Tropsch process and the current market price for crude oil set through OPEC or some independent markets, and then you compare them to the profit you would make through that process, if you compare it to direct sale to these very companies so that they can use the captured CO2, the one that you've captured through DSC in EOR projects. Do you have any idea?
The relation to the EOR project, you have to ask. I just couldn't hear you for a split second. The Fischer-Tropsch is more expensive than oil out of the ground. On the other hand, I would argue somewhere around $70 a barrel, you can actually compete. And you can actually see it nicely that when oil prices in 2008 were above $100 a barrel, many countries, the US included, we're talking about gas to liquid and coal to liquid. The South Africans to this day are running Sasol to make coal to liquid, and Sasol technology is used to take gas to liquid in Qatar. So you see from that the actual Fischer-Tropsch is near the breaking point. If you now say there's a $50 charge for CO2, that can tip the balance. EOR is a complicated story. The politics of this in the US is very, very messy, but outside the US, there's very little EOR with CO2. And ultimately, again, if I charge you for the CO2, it becomes more complicated. I suspect part of the sequestration effort will go through EOR. If you take my approach of saying, let's demand a certificate of sequestration if oil comes out of the ground, then you can say, well, if I pump CO2 in the EOR, I get a certificate of sequestration. And the oil coming out needs a certificate of sequestration, and then we have to find out where you ended up. Now, conventionally, enhanced oil recovery ended up with less CO2 in the ground than carbon coming out. Recently, that ratio has changed to the point that they are sometimes negative. And I think it is the fact that there is a money to be made on the CO2 is gradually shifting the balance. Right? So in the beginning, it's you push CO2 in to get oil out, and the CO2 costs you money, so you minimize it. Now that you get paid for the CO2, you don't try to minimize it anymore. And at some point, you start thinking of yourself as a CO2 sequestration operation, which happens to have a little bit of oil as a byproduct. So you will get a continuum from one end of the spectrum to the other. And I suspect that will be part of the storage issue. And I wouldn't separate that out. But I think the big unknown, in my view, is how much will it cost to bury a ton of CO2? And like it or not, and I'm not in favor of being here, standing here and say the fossil fuel industry should survive. Like it or not, if it turns out I can dispose of a ton of CO2 for $3, the world will keep running on fossil fuels until they run out. And if it turns out that the cost of storage is $100 or $50 a ton, I think the markets will favor renewable energy because it's getting there. And the Fischer-Tropsch is another one of those things where nobody knows what it will cost if it's done at very large scales. Part of the problem you have here, all of these plants are $5 billion investments, and you are stuck for 50 years in a world in which the oil prices can go from 120 to 20 in a matter of a year or two. Nobody in its right mind invests into that. In a world in which you have carbon constraints, which put a floor under this is a very different discussion, and I can't really answer it. The SO2 and NOx, yes, we will absorb those, but I think we can, because these are ion, I'm reading the question in the, sorbents as well as membranes will bind other sour gases. Because they are ion exchange resins, we can actually clean them. But the fact of the matter is 1 in 1,000 sour molecules in the atmosphere is an SO2 and not a CO2. So you have to be willing to live with that. And if your sorbent can't handle that, you didn't have the right kind, because you need to survive 100,000 cycles. What we found out is that because it's an exchange resin, we can exchange the sulfate and nitrates out for carbonates, and then the system is just fine again. But after so many thousand cycles, you have to do that.
Right, thank you. Also, one more, another people waiting. So, Roman, do you have any question?
As I said, I have nowhere to go. My wife had to go to California. I'm here by myself. I can eat dinner whenever so I have time to ask questions.
All right. So, Roman, go ahead.
Yeah, hello. Can you hear me?
Yep. I can hear you.
Yeah, Professor Lackner, thank you very much for your talk. And first of all, I want to thank you not only for your science, but for your publicity and advocacy for CO2 capture and direct air capture in particular. So I have two questions, but probably very short questions regarding the moisture swing sorbent. So you mentioned, like, you made a techno-economic assessment and it needs to survive like 100,000 cycles. Can you give an idea how much mass of the sorbent, or how much kilogram of CO2 1 kilogram of sorbent should cycle through its lifetime? So this is the first question, because I'm interested to understand how much materials we should have in order to handle all that CO2. Yeah. And the second question is, you mentioned that adsorbent pre-concentrates only to 5%, and then you need some other technology to pre-concentrate to compressible CO2. So what is that other technology? Thank you.
Okay, let's begin with your first question, lifetime. This is not limited to moisture swing. If you look at any of those amine-based sorbents, and many of the exceptions are salts like potassium carbonate. But any of those organic sorbents, whether you look at Georgia Tech or us or everybody, they have millimoles per gram capacities. And we can talk about half or 2, maybe 3 on the outside. These ion exchange resins are around 1 millimole of CO2 they can bind, but they have a charge capacity of 2. But you need, for going from carbonate to bicarbonate, you only get half of it. So you're talking about a millimole. That would be 4% of your weight, right? Per gram, or a mole per kilogram. So it's 44 grams out of 1,000. So that's 4.4%. In practice, nobody gets a full swing from empty to full. So therefore, we, in our simple-minded model, we of course have a parametric study, but in the simple-minded case, we say, your swing is roughly 1%. That means a kilogram in 100 cycles collects its own weight. In 100,000 cycles, it collects a ton. Therefore, the price of the sorbent will punch right through to the price of the CO2. And a kilogram price of the sorbent is the ton price of the CO2 if you bought 100,000 cycles. Now things get worse if you allow for the discount rate and you pay interest. So if it's a very fast cycle, you may not care about that. But if it's a very long cycle and that stuff lasts 20 years, you have to double that number, roughly speaking. So bottom line is, at 100,000 cycles, give or take, figure that for every gigaton of CO2 you collected, you spend a megaton of sorbent.
I see.
And that puts you at the 10% level of the polymer production, which is a typical number. We'd be 10% of the water consumption, we'd be 10% of the energy consumption, we'd be 10%. And I'm a little flippant about this right now, but order of magnitude, we are a big player like the aviation industry, like the car industry, but we are not anywhere sticking out either as saying this is orders of magnitude more than anybody ever did. So that's where the sorbent issue is. Your second question, can you repeat it?
Yeah, it was about the, how you pre-concentrate, like once sorbent has done its work. Yeah.
The first observation is that we are not alone in that, because nobody likes high temperatures unless it's carbon engineering, right? And if you look at limiting your temperature to boiling or less, the remarkable feature of any sorbent is that the delta P you can achieve at a fixed delta T is only a function of the entropy change of the reaction. It does not depend on the enthalpy change. Now I can easily play around with enthalpy changes. I cannot really change the entropy change because it's dominated by the fact that I go from a gas to a solid. So within a factor 2, my delta S in the reaction is fixed. As a consequence of that, I cannot really drive the PCO2 up by much more than a factor 100 if I stay below 100 degrees C. So I'm stuck somewhere below ambient. And therefore I have to need to figure out how to get out from there. So the first thing we said, of course, now we look like flue gas and we use a second sorbent and this is all fine. We have worked out how to put it into a potassium carbonate solution and then make bicarbonate. All of this is fine. This is effectively what the membrane system would do. But ultimately, we found that for our particular design, the most economic way of going about it is to pay the penalty of evacuating the chamber with a sorbent in it, then make it moist by letting water vapor in. And you can, by the way, by making it warm, you can control the temperature a little higher. And so you now end up at somewhere between a few kilopascal and half an atmosphere of a gas mixture, which is predominantly CO2 and water vapor and traces of residual air you didn't get out of the system, and that you can fairly conventionally process up. Now we are starting to try to get clever by minimizing reliance on sources of low-grade heat we don't have. But that's a whole long story.
I see. Our
long-term goal is that we can run on intermittent solar energy so that we can get cheap electricity and not pay full fare.
Thank you very much. Thank you very much.
Okay, we have one more person who want to ask questions. So please, Ms. Arai, can you turn on the microphone and then ask question, please? Arai-san, please. Okay, I think she may not be here. Can you hear me, Arai-san? Okay. Can you unmute? Okay, I think she may not be here because she raised her hand, but she may not be here. So because of time limitation, I try to finally ask you because this seminar is very rare because what I'm saying is that some of the Japanese cabinet office member joined this seminar. So this is very rare for us. That is why I would like to ask the Professor Lackner to give us some comment to the Japanese government member, cabinet office member. Do you have any message or comment or supportive comment?
Well, that's a bit of a surprise to being asked and an honor. I would say this is one of the biggest challenges, not the only, but one of the big challenges which will face us in this century. And it is something for the world community to do. this is not something individual countries can solve by themselves. And the more people help and the more people set a good example, the more likely we are to get through this in one piece. My personal view is it is too late to get out of this without any damages. Analogy I've made, we're in a car which is going way too fast and we're going to hit that guardrail. The question is, will we roll the car or just rip the fender off? And it is now all of our efforts which can make this work. And if we can build international collaborations, the more people work on it, the better off we are. This is not something where we should view this as somebody's purview. And I think the more players we have, and I'm quite serious about the possibility of thinking of this as a direct air capture, as a technology whose cost needs to be brought down. So we are just trying to publish a paper in which we argue it is $500 right now, because Kleinworks has demonstrated that. If an institution which has the wherewithal says, we guarantee you the difference between $100 and what the current lowest bid is, and you keep competing this bid down. In photovoltaics, this has been enormously powerful because outside the US at least, people have gone out and said, you build us a 50 megawatt station and we guarantee you the price of electricity. That competitive bidding actually reveals the price and therefore lets competition go and the price comes down. They are now between 1.5 and 2 cents a kilowatt hour. So I would argue here too, you make a bid and we can sell CO2. I noticed in Japan, you have a lot in supermarkets as dry ice. You can sell that at $100 a ton. But the difference to 500, somebody has to subsidize. My argument is if we get 300-400 times bigger than we are today, and this follows normal learning curves, we should be below $100 a ton, and then you don't need to subsidize it. And if you actually add it up, because it's only a 1,000-fold increase in size and not a million-fold increase in price, the total cost is actually remarkably small. We came out at $50 million as our best guess, with a very wide distribution. But if you were to do that and make that work, you could at the end say, this didn't do it because for some reason it doesn't learn. And then we know that we are in really bad shape. Or you learned it, and now you know that it can be done at $100 a ton. And then we can start talking about what are the right regulations to get from that megaton a year to the gigatons a year where we need to be. But whoever puts this together, a country who is willing to do that can make this work. And if somebody had this together, I'd join that effort today because I think that's the fastest and best way to harness inventiveness in societies and move this forward. Because this is not really all that highfalutin academic stuff anymore. This is really just like solar energy. You have to do 1 million little things and you need to do them all 5 times cheaper than you did the last time. And as you gradually get down that curve, things will fall into place. And we are within striking distance. And if somebody could put such a system together, and Japan certainly would have the power to do so, and maybe the motivation. In the US, I'm not quite sure. Part of our biggest problem has been that we are caught between a rock and a hard place. And on the one side, people say climate change is a hoax, so we can ignore it. And on the other side, people say climate change solved this way is a moral hazard. So only 3 years ago, there was a paper in Science bemoaning the moral hazard of negative emissions. And basically saying you don't know whether it works. And bottom line is, we got to figure out whether it works. And the idea that for $50 million we could learn that, that's actually very, very powerful.
Okay, right. Thank you very much. Yeah, this is very supportive, so strong message to the Japanese government. So I hope And also because of time limitation, I'd like to close this seminar. But before closing, I'd like to give the microphone to the director, Petros Sophoulis. So please, Petros.
Professor Lackner, we do thank you on behalf of I²CNER, of the science community of Japan. I would like to thank you for this exciting presentation of these new ideas, this new technology that is emerging. And as you very well pointed out, the world advances through disruptive technologies. And indeed, this is a new technology that will disrupt how we will fight this climate change. And as you know, right now we have a new administration here in the United States. We have a new administration in Japan. And I believe there is no time more opportune for this technology to develop. I think this is perhaps the call of our generation. I've seen your slide there. You talk about, if I'm not mistaken, about $1 trillion industry there if this advances full steam ahead. I mean,
Yes.
this means new job creation, right? I mean, this
Yes.
is fantastic. It is a win from every aspect: job growth, job markets. I mean, and the climate that we want to steward. So I'm with you, and I thank you for this wonderful perspective that you gave, not only from the technology aspects, but also from the techno-economic aspects. And now I believe the ball is, as I say, is on our government's court. If they think that this is the way to go, right? And I think when you put out a compelling argument here, we, the scientific community, are ready to raise to the challenge and do the job. Get that price, as you pointed out, down to $100. Yes, we will do it. Thank you.
Thank you. It was a great pleasure to join you, and I only wish I could have come and visit. But it's nevertheless the modern world which allows you to do this is quite spectacular too. Here I sit in my home office and have a talk with 100 people in Japan.
Well, I do take this opportunity to invite you in Fukuoka, right? As soon as we all get vaccinated, I mean, both in Japan and here in the United States, hopefully by this coming September, we will all get vaccinated so we can meet in person and have profound scientific discussions, right? I look forward and I offer this invitation to join us in Fukuoka. It's a wonderful city, and Professor Fujikawa there, as you know, is pushing ahead toward this technology.
Yes, and if I can be of any help, let me know. I will do what I can to accelerate it wherever and however it works. Thank you so much for the invitation, and thank you so much for your hospitality, and I'm looking forward to future interactions.
All right, thank you very much. All right, so almost time. That is why I'd like to close this seminar. So I'd like to thank all Professor Lackner and all participants to join this seminar. Thank you very much.
Thank you.
Thank you again.
Thank you.
Okay, seminar is closed, so you can